Hello dear students, let us continue with phenols. Today we will be discussing the reactions of benzene ring. Because of the presence of the aromatic benzene ring, phenols readily undergo electrophilic aromatic substitution reactions. And as OH is an activating group, it undergoes these reactions at a much faster rate than in benzene. Additionally, OH group is ortho-para-directive. Therefore, the incoming nucleophile goes to the ortho or para position. Consider this equation: phenol reacting with an electrophile E+. The incoming electrophile can either go to the ortho or para position as shown here. Let us explain it with the help of certain examples. First is nitration. We are giving nitration of phenol under two different conditions. First is the reaction of phenol with dilute nitric acid at a very low temperature of 240 Kelvin. The reaction gives a mixture of ortho-nitro and para-nitrophenol. However, in the presence of nitrating mixture, which is a mixture of concentrated HNO3 and concentrated H2SO4, it undergoes nitration to form 2,4,6 trinitrophenol or picric acid, a industrially very important compound. Next example of aromatic electrophilic substitution is bromination. Again, bromination take place under two conditions. Phenols on reacting with bromine in carbon disulfide or carbon tetrachloride at 240 Kelvin will give a mixture of ortho and para-bromophenol. However, if the reaction takes place in bromine water, vigorous bromination takes place to form 2,4,6 tribromophenol. Last example is sulfonation. When phenol is treated with concentrated sulfuric acid, it gives a mixture of ortho and para-hydroxy benzene sulfonic acid. So that is all in the electrophilic aromatic substitution section. Next, we move on to the special reactions of phenol. First reaction is Reimer-Tiemann reaction. Let us look at the statement. When phenol is refluxed with chloroform and sodium hydroxide at 340 Kelvin, ortho and para-hydroxybenzaldehydes are obtained. Let us look at the equation. Phenol react with chloroform CHCl3 in the presence of caustic soda or NaOH at 340 Kelvin to form ortho and para-hydroxybenzaldehyde. This reaction is an example of orthoformylation of phenol. Moving on to the mechanism. The mechanism consists of two steps. Step 1 is the generation of the electrophile. In this, the chloroform react with alkali KOH or NaOH, and the alkali abstract the hydrogen from chloroform as a proton, thereby resulting in the formation of a carbanion CCl3-. In the next step, one chlorine leaves as Cl- ion. resulting in the formation of a carbene known as dichlorocarbene. So the electrophile generated here is dichlorocarbene. Step 2 is the attack of electrophile on phenoxide ion. Phenol molecule in the presence of KOH or NaOH exists in the form of a phenoxide ion. Phenoxide ion, being electron rich, attack the electron deficient dichlorocarbene in this manner, by which the dichlorocarbene part gets attached to the aromatic ring. Now, if we carefully look at this intermediate 6, it has lost its aromaticity. Now, in order to gain the aromaticity, a hydrogen present here leaves as a proton, thereby resulting in the formation of phenoxide ion 7. This phenoxide ion, in the presence of alkali, is hydrolyzed and one of the Cl is replaced by OH. Because of the proximity of a hydrogen in presence of an OH minus or O minus, this hydrogen gets attached itself to the O minus ion, thereby resulting in the formation of orthohydroxy benzaldehyde, or popularly known as salicyl aldehyde. The next special reaction of phenol which we are dealing today is Kolb reaction or Kolb-Schmidt reaction. Statement: phenol reacts with carbon dioxide at 400 Kelvin and under pressure to form salicylic acid. Equation: phenol in the form of sodium phenoxide react with carbon dioxide at 400 Kelvin and at pressure to form phenyl sodium carbonate. What happens is that the CO2 molecule gets inserted between oxygen and sodium atom. Thereby, we will get OCOONA. This compound is known as phenyl sodium carbonate. This is an unstable compound. It rearranges itself. That means a hydrogen from the ortho position migrates to the oxygen, and COONA from oxygen migrates to the position of hydrogen, thereby obtaining C6H4OH, COONA, which is sodium salicylate. Sodium salicylate on hydrolysis in the presence of any mineral acid is converted into C6H4OH, COOH, which is known as salicylic acid. So that is all for today. We have gone through reactions of benzene ring, that is electrophilic aromatic substitution reaction, and we have seen two special reactions of phenol, which is Riemann-Tiemann reaction and Kolb reaction. So thank you for listening to me. Until we meet again, take care and bye.